There are 4 different ways that we can represent any chemical scenario. The first is to include an energy value as a term in the thermochemical equation. This means that the energy is going to be right in the equation as either a reactant or a product. Here's the first scenario. The combustion of 1 mole of methanol releases 726 kilojoules of energy. The fact that this tells us it releases means that this is a product. It is produced from the reaction. In combustion, we're going to have the methanol, which is the fuel, react with oxygen, and it's going to produce carbon dioxide and water. So there's the balanced equation. We have our methanol, our oxygen, water, and carbon dioxide. Now this is balanced using fractions in this case because we're interested in 1 mole of methanol. And when 1 mole of methanol reacts, 726 kilojoules of energy is released. It's here on the product side. Reactant side, product side. So having that amount of energy right embedded into the equation is one method. Notice that there's no per mole here. We do not write that because we read all of this together. We can see that this is 1 mole. Let's say, for example, that you hadn't balanced it with fractions, and instead you had said, let's see how we do that. If we multiply everything by 2, we would have 2 CH4O. 3 halves times 2 would be 3 O2 molecules. That would get 4 H2O gas, and we'd get 2 CO2. Well, we can't leave this at 726 kilojoules because now as we read the equation it's for 2 moles of methanol. So we would have to multiply that 726 by 2 and you'd get 1452 kilojoules. So either of these is acceptable, but all of the information has to fit together. This amount of energy for 1 mole, twice the amount of energy for 2 moles. So that's one method. Another way to write it is to write the chemical equation, leave a space, and then to the side, to the right of it, state delta H equals, and write the amount of energy. Now when you write it this way, we need to have a negative or a positive here because this negative tells us it's exothermic. If that wasn't there, if you had just written 726, then I would read that as a positive amount, and a positive delta H would mean that it was endothermic. But it's not. It's exothermic. Energy is released. So that's another method. You have the balanced chemical equation, and you have the delta H. Now again, there's no per mole written here because these 2 pieces of information go together. When I read the equation, this is per 1 mole. That amount of energy released per 1 mole of the methanol. Another way is to state all the information. Delta H, a combustion, tells us it's a combustion reaction. It's exothermic, 726 kilojoules. Now this is where we do need to emphasize that's per mole of methanol. Methanol combusting. The final way is a potential energy diagram. So here we have potential energy along the y-axis, reaction progress. You can think of that like time. Here's the beginning of the reaction. Here's the end of the reaction. Well, because this is an exothermic reaction, the potential energy of the products needs to be less than the potential energy of the reactants because energy is released overall. A little bit of energy is required to get this started, but then a lot of energy is released. And the difference between the potential energy held in the bonds of the products and the potential energy held in the bonds of the reactants, that difference right here is our delta H value, our change in enthalpy. and it is 726 kilojoules. And this needs to be a negative value because it is released. So those are the 4 different methods of representing chemical equations. We'll do another example. The formation of diborane from its elements requires 36 kilojoules per mole of energy. Okay, well this here, the B2H6, is a product because it's saying it's formed. We're forming it from its elements. Well, what 2 elements make this up? Boron and hydrogen. It requires 36 kilojoules per mole of this product being produced. The fact that it requires energy makes it endothermic. The energy is a reactant. So here's the first method to include the energy as a term. So boron exists as a solid at standard temperature and pressure. Hydrogen gas is diatomic. We have our energy needed. We get 1 mole of this, and I have balanced the equation appropriately to make that all connect together. Another way is to write the equation and then state the delta H value over to the right. Now this time it's a positive value because this is an endothermic reaction. Energy is being put in. Here we can state all of the information. Delta H of formation. A formation reaction is any substance formed from its elements as they exist at standard ambient temperature and pressure. So to form diborane per mole, we need to put in 36 kilojoules of energy. And representing this in a potential energy diagram, we have our potential energy, we have our reaction progress. When we think about the fact that this is endothermic, energy needs to be put into this. The potential energy of the product is going to be higher than the potential energy of the starting reactants. Here's our activation energy. A lot of energy is needed to be put in to make this happen. We get a little bit of energy out, and now this is the difference between the potential energy of the products and the reactants. That is the delta H value. And we need to state that that is positive 36 kilojoules.